has your experience with Canvas been better or worse so far than Moodle?
That's a great question. Compared to Moodle, I think Canvas is okay. It's not as efficient. I don't know if that's because I just started using it. Maybe if we've been using Canvas all along, switching to Moodle, I would have said the opposite. But one feature that Moodle had, which was just really intuitive, was you could just drag and drop stuff onto this really, really well. And you can drag and drop right here, but the moment I do it once, that field goes away. So you have to click on plus, you have to browse through files, create the file, find it on your computer. It's just a huge hassle out of nowhere. Other things I've seen kind of weird about Canvas is usually you could view your Moodle page and make it look about what this like the student sees. If I do that here, view as student, it just looks horrible. There's this big purple bar that makes it look like we're in the wrong spot or there's something that's popping up we have to throw away. So I feel like it's okay. It's a lot to get used to, but it'll do the job. I don't know if they're saving money on this or it's just easier for IT to implement, but I think if I was doing more advanced stuff in Canvas, if I had like quizzes that were interactive that you were doing inside there, if this was a literature class and you all had to get in some kind of group chat and work out some sort of discussions, more advanced stuff, Moodle's falling really bad, failing really bad. So I think it's a major reason for the university as a whole to adopt Canvas over Moodle. For me, just doing basic things on here, it seems worse, but we'll get over it. Other questions so far? Okay, well, welcome back, folks. We're finishing at week 2, and we're nearly done with the section 1.3 notes. We may finish section 1.4, but the due date of September 16th kind of suggests I think this one will finish off at the very end when we come back on next Tuesday. We'll see where we end up. It's hard to predict exactly how class goes every time. Other announcement is we have our first homework set due today. Again, there's lots of ways people are participating and submitting homework. If you're in the in-person class and you did this as a hard copy, feel free to just drop your assignment towards the desk down here at the beginning or end of class. If you are participating in the fully online section or in the in-person section and you just like to work digitally, then just convert your file to PDF, send it to my ISU email address. Or if you're in the online section and you're working traditionally, but you notice there's no way to upload your homework, all you're meant to do is, if you have your homework done on paper as an online student, just either scan it, take a cell phone picture, and send it to my ISU email address. And that'd be a great way to turn it in. But we'll have more assignments that are coming down the line. We had kind of a slow start on the very first week of class. So there's going to be 4 assignments once this section's finished out. And for the upcoming exam 1, I'm going to be posting information across this weekend, probably Saturday or Sunday at the latest. I'll post information here on the definite coverage, what you can expect to see exactly on exam 1. I'll be posting review problems as well if you want some extra work to make sure you're up to par for getting through the exam 1 questions. Best way to prepare for exam 1 is really just being diligent on the homework. My exams are highly based on and motivated by the homework problems themselves. In fact, we've been constantly kind of hinting this one is a typical exam question and so on. So the more up to date and current you are on the homework, that's the best way to prepare. I'll talk more about preparing for exam 1 as we get, say, to Tuesday, more likely Thursday of next week. But any questions at the moment about it?
For the homework, I just sent it through Canvas. There was an option for like comments, and I uploaded my PDF through there. Would you prefer it
Wow.
through email, or do you think that would work?
That's a good question. I'm like we were talking about at the start of class, pretty new to Canvas. So let me make a reminder here and I'll just follow up back with you. So reminder for me, here's what it's going to look like. Find out how to download homework when uploaded. You said uploaded to the assignment as
Like
a
the assignment comment section.
in the assignment comment section. Okay, I'm gonna look into this and see if I can find it. And if I find it, you'll be all set. And I'll also email you back to double check with you. If I can't find it, I might just say, send it to my ISU email and see what else I can learn about the system to make that just more clear. But this is pretty educated for me. Probably that's the best way for people to do it. So I'll look into that. Thanks for mentioning it. Other questions so far? Sounds like Canvas definitely has a lot more interesting features than even I was aware of. So this will be kind of interesting to look into. Maybe that's the best way to do it. Usually I'm an email guy since email's been the way I've been operating for about the last 15 years at ISU, but that might be the most intuitive way to operate going forward. Well, any last questions or comments, folks, before we get started? Okay, well, let's begin. We're in section 1.3, nearly done with it. The new thing here is we're talking about vectors, system of equations written out as a vector equation, and the big content, linear combinations and spanning. So here's our first pretty big definition, I'd say. Spanning is the major one in this section, and linear combinations is just a core component of that overall definition. Let's read through it in full, see what it's saying, and just write out a quick example to go along with it. It says, if you have a list of vectors, v1, v2, and so on through vp, ... is going to be in a lot of definitions since this is going to be an inspecific size of a list. They all come in Rn. So every one of those vectors, v1 through vp, has n components. And scalars, c1, c2 through cp in R. So this could be 0, 1, pi, and so on. Then the vector y, defined in this way. Y is the result of taking c1, scalar 1, times v1, vector 1, add the next one, scalar 2, scalar multiplying v2, so add here is now vector addition, and so on to the last scalar multiplication, adding these all up. The result y is called a linear combination of vectors v1, v2 through vp, using scalars, or sometimes the author says with the weights c1 through cp. So lots of things going on in this definition. We have vectors, we have scalars, we have scalar multiplication, vector addition, and a vector equation. Y just happens to be the output. And we say Y is the linear combination. So to track through all these kind of components, let's just do something as a small example, a quick announcement or a quick representation of this. Let's say let V1, V2 in R2, so simplifying this a bit to understand the definition. I used the set inclusion symbol, but usually I'm going to just write out in literally that V1, V2 in R2, V1 is 1, 5. V2 is equal to -3, 0. Let C1 equal 2, C2 equal 1, be scalars. That's kind of a redundant statement to say let C1, C2 be scalars, because the moment you say C2 is equal to 2, or C1 is equal to 2, C2 equals 1, you've said they're scalars already. We're just trying to track through the definition, so we're being redundant on purpose. Then Y equals 2V1 plus 1 times V2 is a linear combination of V1, V2, using the scalars 2 and 1. So here, this would be the C1, this would be the C2, and we just stopped. They didn't simplify here. We're just mainly saying this is what a linear combination looks like. If we were doing more work with the vector y, we might work out what this is exactly. And essentially, that's all we were doing right up here on this example. We had vectors u and v. We found scalars 3, -2. And we just wrote out that linear combination. Essentially, the only thing new in this definition is they call it equals y. That's the new part. So this is your typical linear combination. There could be two vectors in R3, two vectors in R2. There could be 20 vectors in R3, something along those lines. And a larger question about all of this is, if I grab an arbitrary vector, b, and take these three vectors here, we wonder, could the vector b be written as a linear combination of a1, a2, a3? So that's the next question we're going to address. We have to state our conclusion clearly on this one. So there's really two things we do. A bit of the algebraic work, probably with the augmented matrix you're expecting, and then just a clear conclusion. Yes, it's a linear combination. No, it's not. Well, let's track this a little bit more carefully. Here in the definition, y is playing the role of b. The vectors v1, v2, vp, and rn are a1, a2, a3. And it's just asking, can b be written as a linear combination? It's not saying, if so, what are the scalars c1, c2 through cp? So in other words, let's rephrase the question. Is x1, so now x1, x2 through x3 are going to play the role of the scalars in R. As we write this out, is x1 a1, there's a lot of color coding, plus x2 a2 plus x3 a3 equals to b consistent. So that's the whole original question. This is probably just a more familiar question to us. One thing that takes a little bit getting used to in linear algebra, and the author exploits this when he writes out exercises, is the same question can be just re-expressed in a lot of different kinds of ways. So asking if a vector b can be written as a linear combination of those three vectors is completely synonymous to asking, is this consistent? And this is what we were doing last class. This is now our vector equation. We could express this vector equation as a system of three linear equations and the three unknowns, x1 through x3, or we could just drop right down into the augmented matrix and start solving that thing. As we go to solve it, our major tool we're going to use from section 1.2 is the existence of uniqueness theorem. We're just going to go to echelon form, and if we spot a pivot in the rightmost column where we've augmented our matrix, we'll say inconsistent, it's not a linear combination. There's no such pivot in the rightmost column and the system's consistent. Doesn't matter if there's infinitely many solutions or one unique solution for x1, x2, x3. We'll say it's consistent, so yes, it's a linear combination. So that's how we attack this kind of question. It's kind of technical in a way because there's just a lot going on with this definition. Check the color coding for all these different moving parts. And you have to imagine this is what the question would look like as a homework problem or exam problem. There's not a lot to go on. We just need to know this is the meaning of the question. Can we solve this? So just a reminder, because we're just wondering if this is consistent or not, we need only echelon form. We don't need to take it all the way down to row reduced echelon form. So here's our augmented matrix. Oh, and I accidentally forgot to bring back the participants window. There we go. Sorry about that folks in Zoom. Augmented matrix goes, following the color coding, 1, -2, 2, 0, 5, 5, 2, 0, 8, then augmented here, orange because that's optional if you'd like to put in that dashed line. Then the vector b, which was -5, 11, -7. So up above is the column vectors that we just assembled now into the augmented matrix for the portions on the left, columns 1 through 3. On the right is just the right-hand side now. And now, seems like every class gets down to this some way, somehow. We begin the row operations. Our major goal now is to find all the pivots. Finding the pivot position will tell us everything about consistent versus inconsistent. Any questions before we launch into it? Okay, let's try doing this in a slightly different way. For all the other row operations we've done before, we've been writing down a recipe for how we did each row operation. Some people have done this on the exercises they submitted already. Some people probably haven't or didn't really want to. It's always going to be your call. We were mostly doing that because we're getting used to row operations, so let me know how this feels doing it in this new way. Let's skip the description here and just track through really carefully what we're doing at each step mentally. So I'm going to pivot off this position in column 1. Let's write in row 1 as 1, 0, 2, -5. Now you can imagine just visually, I want to double row 1, stack it onto row 2, adding the corresponding entries, and just write down the output here. So this will be 2 times 1 for 2 minus 2 for 0. 2 times 0 plus 5, still 5. 2 times 2 is 4 plus 0, takes us to 4. 2 times -5 gives us the -10 plus 11, gives us a +1. This is the first time we've done that. Does that make sense to folks on how we got to that row 2? Okay, glad to hear that. Again, if that's helpful to you for you to do it in that way, then proceed in doing it as I did just now. If writing down the instructions is a good way just to kind of organize your thoughts, or maybe go back and check your work just as a reminder on how you form those columns, not a bad habit to just stay in. So this is always just completely up to your preference. Let's try it out again. I want to eliminate that entry where the red dot is, that +2, which means -2 is the number we're going to multiply by. So row 1 multiplied by -2 will give us -2 plus 2 for 0. -2 times 0 is 0 plus a 5 for just a 5. -2 times 2 is at -4. Plus 8 is going to get us to +4. -2 times -5 is at +10. -7 takes us to +3. So just remember that -2. When I do it this way, that's the thing I sometimes get a little bit just mixed up in if I'm doing it too fast. Everything up here is multiplied by -2, add to the entries below, and we're doing the same thing as we've been doing since day 1 in the class. So now we have a pivot in column 1, a pivot in column 2, and the only thing we need to do to get it into echelon form is eliminate that 5 by the red dot. So let's start our next operation. Rows 1 and 2 can copy in directly. 1, 0, 2, -5, 0, 5, 4, and 1. Now we'll start the operation. We just need to subtract rows. So more specifically, multiply row 2 by -1, add to the entries below. So carefully tracking that. This will be -5 plus 5 for a 0 here, and forgot to write in the 0 on the left. -4 plus 4 for a 0. -1 plus 3 for a +2. And this is what the system now looks like. We have a pivot in column 1, column 2, no pivot whatsoever in column 3, but we do have a pivot in column 4. Because we augmented this matrix, our consistency and uniqueness theorem, theorem 1.2, sorry about that, let me make this a little bit smaller. There we go. This theorem says the system is consistent if and only if the rightmost column is not a pivot column in your augmented matrix. It's exactly what we did. We augmented with the right-hand side of this system of equations in vector form. Because there is a pivot in the rightmost column, we get to say inconsistent. doesn't answer the question, so we have to clearly express our answer. So that's the emphasis here in brackets. But inconsistent now tells us, let's write here, right arrow just a way to say implies B is not a linear combination of A1, A2, A3. You might have just said inconsistent, not a linear combination. That would have been okay. But sometimes it's not a bad idea to just say it all at once because you really are connecting a lot of information in your head doing this kind of problem. The more you really just say it out, write it out, the more all these thoughts start to go together. You will have more traction on your mind for this kind of problem. Recall will be a lot easier later on. Well, we did it, folks. That's not the toughest question. Really, it's just a redo of prior questions written in a different way. We're talking about linear combinations. There's vocabulary on top of it. And it was more about the vector equation, less about a system of equations this time. Any questions whatsoever on the solutions here? Solution here?
This means that those three vectors would have to be in the same plane.
Exactly. If we had a yes here, well, maybe a better way to answer that. If there was a pivot right here, that means those three vectors do not form a plane. They sweep out all of R3. We'll say the three vectors would span R3 if there's a pivot right here in that position. The fact that there's two pivots means when we span these vectors, look at the set of every possible linear combination, it just forms a plane in three-dimensional space. If there was one pivot, that means every linear combination of this set of three vectors, every one possible, forms a line in three-dimensional space. Whether it's a plane or a line, it will always go through the origin in three-dimensional space. Other questions about that so far? Okay, lots of interesting things going on. And again, this is kind of a small component. Linear combination is the key to understanding this idea, spanning. So just to get those two thoughts related, I put in a remark. Example 5 could be rephrased as saying if B is a linear combination of the columns of A. So this could be specifically columns of A, or we could have been just talking about the vectors as well. Let me put a little break there to kind of disconnect that thought. And the major reason for this big wall of text this time, sorry about that, is more just to get linear combination in view of this brand new definition. It's part of the star of the show because it's used to define spanning. We harped on this just a little bit last class, but emphasis is really important. This, I mean, it's debatable here, but if I had to pick the most important definition, not theorem, something like this is more of a theorem, for example, just a statement of mathematical ideas. But as far as a core definition, I would say this is the most important. Core definition in linear algebra. Again, that's really debatable. Depends on what level you're studying linear algebra at. In introductory linear algebra, our class, this is the main idea. Being successful in this class, in a real sense, is going to be predicated on how well are you able to understand what's being said in this definition, because then you'll be able to apply these ideas better. You'll know what the questions are really asking. It won't feel like you're just pushing symbols around, pressing I believe every time you just run through an example or do some reading. So we'll go through this really carefully. If we spend extra time in section 1.3, based on my big statements right here, it would have been time well spent. And we previewed this below. In one way, it's a core definition is spanning itself is one key to define a basis for a vector space. And eventually we'll be able to say, once we know what a basis is, what the dimension of a vector space happens to be as well. So we have this interesting stack of cards, or house of cards rather, for our definitions. And spanning is one of the big pieces of that puzzle. So let's read through the definition. I have different ways of thinking about it. First, here are the author's words. We grab vectors v1 through vp in Rn, so maybe two vectors in R3, for example. Then the set of all linear combinations possible of v1, v2, vp is going to be denoted as the span of v1, v2 through vp. We indicate it this way symbolically, just span and curly braces because it's a set, a mathematical set or collection of objects, and then just comma separate those vectors. It's a subset of Rn in the sense that every vector here is in Rn, and if it's a linear combination, it stays in Rn as well. So it's the subset of Rn spanned by v1, v2 through vp. And that could be it. That could be our whole definition. That's kind of technical because now it's all in words. It could be really hard to visualize. So here's another way to think about it. The span of v1 through vp is a collection of all vectors that can be written in this form. c1 times v1 plus c2 times v2 plus cp times vp. The reason we can write it this way is that's what a linear combination of v1, v2, vp looks like. Sure, I don't have y equals, but we never required that. This is the core essence of a linear combination. It's a way we combine the vectors with scalars, doing the scalar multiplications, and then all the vector additions throughout. Yet another way to think about this, set notation turns out to be pretty important in linear algebra, which makes the structure of our classes in the math department a little bit weird. If you haven't taken a class that discussed, if you haven't taken a class that discussed set theory, maybe 1187 or the more advanced version of that in the math department, I forget the exact course number, then set theory might be kind of mysterious at first. So we'll discuss it a little bit, the elements that we need for this class as we go. The curly brace like this, just highlight this one, it's just a way to say a collection of objects. So it's a mathematical set where order is not important, except that we do have things indexed in a certain way. There's a definite first vector, definite second vector. When we say we are spanning that set, it means we're constructing a brand new set, the one we see on the right. And this is a so-called set builder notation. We need set builder notation because if these vectors are not the zero vector, there's by default infinitely many vectors inside of here. And we'll see that once we start to visualize the span of the set in the next exercises. So the way we write or read this out is, we say that this is the set of linear combination C1 through C1 times V1 plus C2 times V2 through CP times VP. Colon here is read as such that there's a condition to get this thing. The only condition we have is that C1 through CP are scalars. In other words, they're in R. But notice there's no big condition on that. We just say they're in R. It's kind of like what we said above here. Let me go to the right part. X2 is in R. A meant it could be anything. X2 is free is also expressed in this way. So when we just say X2 in R, or when we say C1, C2 through CP are in R, that means any scalar whatsoever. Pick 0, 0, 0. That's one linear combination inside the span. Pick 1, 1, 1. That's the second one. But there are infinitely many choices, much like there are infinitely many values in R. And any combination of those gives you a vector here inside the span. So big definition, we visualized it in 3 different kinds of ways. Any questions so far? Okay, it's tough to really internalize this definition, so we're going to do a couple things. First, we'll just illustrate it. That's what example 6 is all about. Just run through this definition again. Let me scroll to maybe this part as we do that. So the set theory definition. This one's pretty similar to a homework exercise as well. It says list 5 vectors in the span of V1, V2. So we're working inside of R3. All of our vectors must now be in R3. Here's the V1, here's the V2. And I think these instructions are pretty close to verbatim for the homework set. For each vector, show the weights on V1, V2. Recall weights, as our author uses sometimes, is synonymous with scalars. Our author has a knack for saying one way, one thing 5 different ways. Used on V1, V2, used to generate the vector, and list the entries of the vector. Honestly, these instructions are really vague. And so when I first assigned this problem, people really were not sure what to do. Makes sense. I get how this is a pretty vague question. So when you see this again in the homework, return to here just to see what's really being asked of you for this kind of question. So running through the definition, if I want 5 vectors inside the span, here's what they would look like. Here's vector 1. I'll just list this out as 1 through 3. This could be, let's call this y1. It kind of reminds us that y equals various things was our first definition of a linear combination. And span is nothing but the set of all linear combinations. How do you get a linear combination? You pick the weights, C1 through CP. So we literally have to pick something, which makes this a weird problem because it's completely open. You could be supremely creative. You could work really hard on this, or you could work not so hard. Good set of weights could just be 0, 0. I'm going to pick 0 for C1. Let's color code this just a bit to show how they go together. So 0 times V1. Then I'm going to pick 0 for C2. So it'll be 0 times V2. The rest of the definition is irrelevant because we have just 2 vectors. This is just the general way you would write an overall definition. So there it is. It says show the weights. We showed the weights here and here. List the entries of the vector. All they're saying here is actually write this out. But 0 times V1 is just 0, 0, 0. You're really multiplying all the entries by 0. 0 times V2 is just 0, 0, 0. So we're taking, doesn't hurt to write it out, 0, 0, 0 plus 0, 0, 0 equaling 0, 0, 0. Or you might have just written the 0 vector like this, and that would have been completely fine. So either way you'd like to say it, listing the entries or using our shorthand notation here for the 0 vector is fine. And this is vector 1 inside the set of span V1, V2. Already this is kind of telling us something important. The 0 vector is always in the span, no matter what. Span any list of vectors whatsoever, I guarantee you the 0 vector is in there because we can always choose 0 as the scalars or the weights on each vector. So that's an important fact. If you're ever asked to list vectors inside the span, that's the freebie, the 0 vector. Any questions so far, folks, with listing out these vectors? Okay, we're going for 5 of them. That's a lot. If this was a real exam question, I might have just said list 3 and then we move on to the next. I think 3 does the job to understand the concept. Well, let's go for the 5. It says it here, so let's do it. But again, you never have to work too hard. Y2 is going to be a linear combination. Span is the set of all linear combinations. And it's formed this way. You just grab whatever scalars you want. If you like the trick with 0, 0, then just build off of that. How about 1 and 0? So I would go 1 times V1. That's a valid scalar. Might as well use it. Plus 0 times V2. And your job is done. Well, 0 times V2 is just 0. We don't have to show that this time. 1 times V1 is just V1. So if you ended this by saying equals V1, I would say that's completely fine. It's not following the instructions to the letter though. Notice it says list the entries of the vector. So let's be hyper literal on this and just actually list them out. V1 is 1, 0, -5. Already, this is the next second key fact. This goes with parts 2 and part 3 of this. V1 and V2 are in span of the set of vectors V1 through V2. Likewise, up here on the core definition, 0 vectors in there by default. So is V1, V2, V3, and so on through VP. It contains the 0 vectors, it contains the original vectors we're spanning, and infinitely many more. So let's just write out part 3, or vector 3. It's Y3 because it could have been something different if we weren't expecting this. So I'll just keep this pattern as we go. Take the scalar 0 times V1 plus the scalar 1 times V2. From that, we just get V2. And just to be super specific, because they asked us to, we're just being nice. Let's list the entries. V2 is -2, 5, and 0. We ran out of all of the freebies. So this is where you could get pretty creative if you wanted to. Here's the 4th vector, Y4. All you need to do is fill in the blank here for vector V1 in the scalar multiplication. Fill in the blank here for vector V2. That scalar multiplication, work it out and your job is done. Some people might have gone 10, 20. If that's you, that's okay. That's a bona fide vector, you being creative. Other people might have decided, well, why not 0? We love those zeros. It's just going to simplify the algebra. And 2. That works just as well. That's a brand new vector, right? If you went 1, 1, 1, -1, 5, 4, all those are completely fine. You might need to do a little bit of extra arithmetic and to work it out. But going this way, it's kind of nice because what we get is nothing on this one. That's just the 0 vector. 2v2 just means we scale this one by 2, so it's -4. 10 and 0. Takeaway here is you don't have to work too hard unless you want to. There's no harm doing that. We just need one more vector. So here's vector 5, call it Y5. And I've been kind of hogging all the choices here, so I'll leave this one up to the class. Any volunteers for a choice of the scalar on V1 and V2?
You just do 0.
Absolutely, that's a fine choice. Thanks for submitting those values. That would be my favorite choice as well. There's no reason to work too hard. Other people might have gone -1, 0, anything like that is terrific, I'd say. So if you go this route, 0v2 is gone. Adding a 0 vector doesn't change what's over here. And the result is, scale this by 2 for a 2, 0, -10. So all 5 of these vectors belong to the span V1, V2. There are infinitely many vectors in here, and so we can't list all of them, but at least we have an idea of how does a vector get inside there in the first place. It's all about this. Just take a linear combination. Any questions so far, folks, on this more algebraic-y way of thinking of span? Okay, well, let's do some more along these lines. There's the core definitions, really kind of technical, kind of analytical. There's us just literally writing them down, but still, this might be kind of hard to visualize. This is in 3-dimensional space. And it doesn't really give us a good view of what is the span of V1 and V2, if we're thinking geometrically now. There have been some hints about this in the class already. It could be a line, it could be a plane. 2 vectors should determine a plane. You might have better intuition of that if you're taking or have taken Calculus 3. It's not always the case. It depends on the vectors are linearly independent or not. All about the pivots, really. So there's more to that story. Let's start doing some of that kind of work. Because I'm not a great artist, let's work a little bit smaller of a space. Let's work inside R2 and sketch the span of one single vector. You can have a span of any list number of vectors as long as it's finite. Oh, sorry, I missed a chat. Joel said, are negative V1 and negative V2 in a span V1, V2? Yeah, absolutely. Those would have been really good choices as well. Honestly, when I went with 2 times here and 2 times there, your choices of a negative V2 and then a 0, and then a negative V1 and a 0, that would probably have been even simpler. Those would have been great choices. Other questions so far? Okay, well, let's give this another try. Now, just thinking more geometrically this time, I'll leave it to you to the reading where there's excellent graphics and discussions on what some of this kind of stuff looks like in 3-dimensional space. So we have V1, V2 as a vector we're dealing with. We're interested in the span of V, and this is going to be an R2. So let's just draw the 2-dimensional plane. Here's my visualization of R2. Instead of calling this an X and Y axis, we'll call this an X1, X2 axis. In 3-dimensional space, instead of X, Y, Z, we're more liable to call it an X1, X2, X3 axis. The vector in question is 1, 2. So we can plot that here. 1 for the first component is going to plot in the X1 direction. 2 in the second component plots in the X2 direction. And here it lies. Here is V. Our goal is to sketch the full span of V. And so really the best way to think about that is look at all possible linear combinations. This time a linear combination of V is just a rescaling of V. So let's write it out this way. 2 times V is in span of V, and 2 times V is just rescaling V to a 2, 4. So that's going to take us 2 in this direction, 3, 4 in this direction, and we end up here. Now just rinse and repeat. Another thing we mentioned is the 0 vector is in the span of any set of vectors. That's because 0 times V, that's another linear combination, equals a 0 vector is in span V. And the 0 vector written this way is just the origin. The X1 component is 0, the X2 component is 0. And maybe just one more. Negative V, like we mentioned, that's just -1 is a scalar multiplying V, which is equal to now -1, -2 is in span V. So now here, if we multiply by -1, -2, we're on the other end of what looks like what's forming as a line. So here's -1, -2. And right in this position is -V. Now, if I have a steady enough hand, this is finally the span of the set. Didn't do too bad this time. Probably didn't drink too much coffee. Looks like an actual line almost. This whole line is now span V. We'll later on say that this is a one-dimensional subspace of the vector space R2. If we were working in R3, we might have a 0-dimensional subspace. That would just be the origin, the 0 vector and nothing else inside that span. That only ever happens if you're spanning just the 0 vector itself, because any linear combination of the 0 vector gives you back the 0 vector. So that's one subspace in R3, or you could be looking at a line in R3, or a plane in R3, or it's just R3 all itself. Some of our goals in the next section is to determine conditions on when those kinds of things happen. If we put our vectors in a matrix and analyze the pivots, it'll tell us what the span of those vectors are going to look like, whether it's a line or a plane or something else in R3 or even R4 and so on. Oh, and I Might have missed a chat, sorry. Brian says, so the span of V1 and V2 is just a way to describe all points on an X1, X2 plane. Let's see. Yeah, so for that question, it's almost true. It turns out it just sort of depends. So for example, let's write down an additional comment here. Span of, let me put in the specific vectors, 1, 0, and maybe 2, 3 equals R2. It turns out the span of those two vectors is in fact all points on the two-dimensional plane, R2, or X1, X2 plane, you might say. But there's more to the story because let's put in a different example. Span of, let's go 1, 0, 2, 0 is not R2. Part of our goal is to tell the difference. What's going on here? These are the sort of questions that the section 1.4 starts to resolve. But this is an excellent and insightful question already. So let's spill the beans on this one. Why is this one R2 and this one not R2? Anyone happen to see the difference between these two? While we're pondering that,
The 3,
let me call this. Oh, sorry, go ahead.
the 3 in V2.
Yeah, absolutely. That 3 is pivotal. That's kind of a pun in a certain sense. Because if we put V1, V2 in a matrix and go 1, 0, and 2, 3, there is a pivot in every single column. Turns out that's the key. That's how we get the span to be equal to all of R2. Whereas over here, if we put those vectors V1, V2, 1, 0, 2, 0, it's deficient of pivots. There's only one pivot here and none in column 2. Looking at V2 really closely, it's just double V1. V2 is a linear combination of V1. We'll later say these vectors are linearly dependent, which is just another way of saying there is not a pivot in every single column here. We'll later on say over here, these vectors are linearly independent. Two linearly independent vectors will span the entire plane. And the whole answer to that story is it's just because there's a pivot in every single column. In our introductory linear algebra class, everything comes back to the pivots. So all of our big definitions we're talking about comes down to, if you row reduce this to echelon form, where are your pivots? But other questions or comments along those lines? Okay, thanks for those questions and comments. That's really exactly where all this kind of stuff is going to. Sometimes the span is just a line, like in this case. Sometimes if you have two vectors in R2, the span is the entire plane, and sometimes it's not. So our current further work into the subject is going to be resolving these things in chapter 1, starting it really quite soon. Before we end and go off to the next section, where it's going to start addressing those burning questions we were having already, here's one last question that's kind of similar to what's going on in the homework. It's also a kind of a geometric question as well, and a reminder, our author can ask the same question with different wording, like 12 different ways sometimes. We have two vectors, A1, A2. A new vector B that we're curious about, and we've hinted at this already. A1, A2, these are in R3. And if things work out just right, the span of these should be a plane. It turns out it is. The problem asserts it right here. The next sections are going to resolve why that's the case. So this is a weird thing to say in a math class. Let's just take this for granted for the moment. The fact that if you do put this in a matrix and there's two pivots upon row reduction will further reveal it. But we're going to say, let's take for granted the fact that the span of A1, A2 is in fact a plane. The only way it wouldn't be is if this one was a multiple of the other. But it cannot be because of the way one goes to -5 and one goes to 2. So it's asking for what values of a parameter h, another new thing here, is the vector b in the plane spanned by a1, a2. Here's one way to kind of resolve this. Span a1, a2 is the set of all linear combinations of a1 and a2. So my way of thinking about this problem, you might not write this down when you attack this on the homework problem, but it's a good way to start structuring how are all these definitions now linking up in linear algebra already in section 1.3. So we want to know if B is in the span of A1, A2, is just verbalized as a plane. But if A1, A2 is a set of all linear combinations, we're just asking, is X1 times A1 plus X2 times A2 equals B. Oh, let me check my wording above. Span of A1, A2 is a set of all linear combinations of A1, A2. I forgot to write in a sentence. Sorry about that. Let's pretend I didn't say this just yet. There we go. It's gone. I want to connect a thought. So the question right here was really just, is B in span A1, A2? Sorry for that weird edit there. I think that's an important connective tissue on where we're going on this. So if you're asking if B is in a plane span by A1, A2, it's really just a question, is B in that set span A1, A2? But since the sets span A1, A2 is all linear combinations, just write down the linear combination right here. Linear combination. Connecting with that thought. So we wonder, is this vector equation consistent for what values of h? That might not be the most completely grammatical statement, but does that make sense with what we've written so far? I think if we put the word and for what values of h, that flows better grammatically. So really it's a similar question as we've done before. All we're now doing is changing the value of h to see for what values is this actually going to be consistent. We address all these kind of questions so far by going down to an augmented matrix. And so here's the big punchline to this. This is just wording to organize our thoughts, but the overall process was, take your vectors, A1, A2, here they are written above, and just drop them into the augmented matrix. 1, 3, 1, -5, -A2. Now it's augmented with the vector B on the right-hand side of this vector equation. 3, oh, let me try again. 3, -5h. And now it's just a row reduction problem. Any questions so far, folks, on the setup? Okay, lots of questions in this course are going to return to this kind of work we're about to do. So that's why we took that extra time on the earlier classes, last 3 classes, just on row reduction as a skill. We're going to pivot off that entry right there, which means copy in row 1 to start. 1, -5, 3. Take -3 times row 1, add it to the row below. We'll get 0 here. -3 by -5 is positive 15. -8 is going to take us down to 7. -9 minus 5 is going to take us down to -14. Now to eliminate the 1 here, take -1 times this row, add to the entries below. So this will be -1 plus 1 for a 0. +5 plus 2 for a 7. -3 plus h, I'll rewrite as h minus 3. And we're off on our way. We have a pivot in column 1, a pivot in column 2, but to determine whether we're consistent or not, it now boils down to, is column 3 a pivot column? Because this is an augmented matrix now. So another row reduction step. Copy in both rows 1 and 2. 1, -5, 3. 0, 7, -14. And that 0 can't change, so we'll copy that in as well. We're taking -1 times row 2, adding it to row 3. So -7 plus 7 for 0. +14 minus 3 plus h is going to give us h plus 11. So we for sure have a pivot here and here. We knew that already on the prior step. Question boils down to, when is that going to be a pivot? Do we even want it to be a pivot? Depends on the wording of the question, right? People and folks shaking their head no. And I agree, if we want this to be consistent, that's how the question is formed here. We want this to be a 0, so it's a non-pivot. Again, that takes us back to, just as another quick reminder, this theorem once again. If the linear system is consistent, if and only if the rightmost column is not a pivot column. To force that in, we want a 0 there. So we'll say the system is consistent. And we can write out if and only if, but if that feels tedious, a good way to just shorthand that is the biconditional arrow. So this is saying whatever happens on the left implies whatever happens on the right, the literal if and only if. And whatever happens on the right will imply something's going to happen on the left. So it's logic that can go both ways. So system is consistent if and only if h equals -11. Put the 0 there, so now there cannot be a pivot. But we have to return to the original question. So now we can say B is in span. You could say the plane spanned by A1, A2, but let's shorthand it to just span A1, A2. They're the same object. Span A1, A2. If and only if h equals -11. So this was our main objective. That's the only way B lands in that plane. Well, any last questions, folks, on finalizing this one? Okay, this is a weird place to pause again. Not everyone has taken or is taking Calculus 3, so you might not be too worried about the equation of a plane in variables x1, x2, x3. But if you have taken Calculus 3 or you are taking it, you didn't need to know the equation of the plane, but what you would have to done is come up with a normal vector, cross product of these two vectors. That's in fact something we do in chapter 6, so that's why we're not going to do too much work on there. That'd be going a little bit astray. Then it's really fast to just form the equation of the cross product and the fact that one guaranteed vector inside the span is the 0 vector. So that makes forming that equation actually pretty rapid overall. But here's where the notes will end. Any last questions or comments whatsoever before we take a preview in the next section? Okay, let's close this out. And I won't take up too much of your time in section 1.4. Looks like we have about 15 minutes and a little bit of change. Let's take a look at some issues of what's going on with the terminology and notation here. And maybe do this matrix product here once, and I'll do it the second way when we come back on Thursday's class or Tuesday's class next week, so that we're not trying to rush through these notes. But another thing I think is interesting to take a look at before we get started on these notes is what some of these theorems are going to start looking like in linear algebra. Theorem number 4 is a really, really interesting theorem. It's going to take systems of equations being consistent, a vector being a linear combination of columns in a matrix A, the columns of A spanning an entire space like Rm, and reduce all of those terminologies and definitions to where are the pivots. Another thing that's really interesting is the logical equivalence. All of these statements are going to be simultaneously true at the same exact time, or they're all going to be simultaneously false at the same exact time. So we look at some pretty odd theorems, especially if you've taken a lot of calculus classes and you haven't seen logical equivalence just yet. So this will be a big part of what we're doing on Tuesday, understanding this big theorem 4. And it turns out to be a special case when your matrices are not squared. A preview again of what linear algebra is getting into. This is section 2.3 as a preview. Is this one. This one is the monster of linear algebra, the invertible matrix theorem, and it actually grows the further and further we get throughout the course. It's taking a whole bunch of concepts, a matrix being invertible, something about trivial solutions to a homogeneous equation, independent columns, one-to-one, all sorts of other things like spanning again, but every one of these really big technical definitions comes down to what are the pivot positions? And this is kind of amazing in a certain sense. Somehow, when you write down a matrix, you row reduce to echelon form and you know where the pivot positions are, all of these statements are going to be true simultaneously, or they are all going to be false simultaneously. So this is kind of par for the course in linear algebra. We're making our first head segue into that on our theorem 4 right here. And to get to all of that kind of stuff, here's the new thing in this class. That's an odd looking equation because A is a matrix, X is a vector of just the right size, and B is also a vector. So this is no longer a vector equation. We'll call it something like this, the matrix equation, AX equals B. Well, this is where the note starts. I just want to give a quick preview of where all this kind of stuff is going. There's a lots of definition, a lot of terminology, and they all get linked up in big theorems of logical equivalence. So we'll take the extra time to really understand how that goes. First thing we have to do is be really careful with what we mean by rows and columns. I was a little bit loose with it in sections 1.3. I was just kind of pointing with a red dot saying column, or pointing with a red dot going that way and saying rows. But now it's absolutely vital because these theorems are talking about rows and columns. We mix them up, we're using the theorems incorrectly, and we're getting totally wrong conclusions out of nowhere. So we have two objects, U and A. We're going to indicate the number of rows and columns in the expressions below. Might as well color code it for emphasis. And then indicate which vector space, we'll define that formally in chapter 4, where the expressions came from. First one's kind of weird. This one we've literally called a column vector already. And this has 4 rows. Going this way, it's kind of hard to put a curly brace like that. 1 column. And then we would say U is in R4. We say R4 because there are 4 entries, or said differently, it's a column vector, 1 column, with 4 rows. So that gives us the R4. We're just being really, really explicit with what we mean by rows and columns because once again, if you look at this theorem carefully, M and N is at the rows and the columns, and it's talking about pivot positions in every row. If we ever mix up what is a row and a column, we are kind of dead in the water with this theorem. Suddenly, it feels like it's way more cryptic than it was ever meant to be. So let's be super, super specific once again and redo this with the matrix A. This one has 4 rows. So the rows are line by line going this way horizontally. it has 3 columns. And this is kind of interesting notation. We would say A is in R. We go 4 to say that there are 4 entries, but now there's 3 columns. So to convey that, we say 4 by 3. And there's more to the story. There's another shorthand that gets used quite a lot in linear algebra, just to show if this operation right here is even compatible. Sometimes these things are just flat out undefined because this is a matrix times a column vector. So one really quick way we write down the dimension, rows versus columns, is we would put sometimes 4 by 1 right here to say this has 4 rows, 1 column. On this one, the quick shorthand that we would write out is this one is 4 by 3 to say it has 4 rows, 3 columns. So in other words, when we go to use that shorthand, this is always number of rows. This one is always number of columns. Really, really critical stuff because we're going to be using these shorthands everywhere we're going in those notes and going forward. We'll be referring to columns and rows everywhere we're going. And this is the first spot in the notes where if we ever got that mixed up, it's actually a very, very bad thing. Theorems are going to fight against us if we get them backwards. Now, next new thing we'll take a look into is a brand new kind of product. We would like to take a matrix. Size m by n is now saying it'll have m rows and columns. Let's just say that one more time to be really specific. Rows here, columns here. The columns we'll just write out as A1 through AN. And because it has m rows, all of those columns are in Rn. Rm. I don't know if I gave that the right inflection there. So if there are m rows, A1 and AN, that's the number of columns, but every single one of those columns has m entries. That's really a lot of little tiny things to keep in line to get this algebra just right. X is in Rn, which was the number of columns over here on the left. And if that's all correct, we can define the product of A times X. If there's a mismatch right here, if X is in R, let's say M, and M is not equal to N, this is an undefined product. So we need to be really careful to check these dimensions. So the product of A times X, just like most things in algebra, is just the juxtaposition, put them together. AX, we mean multiply. But this is a brand new kind of multiplication, so it has to be defined. And it's the linear combination of the columns of A using the corresponding entries in X as the scalars or weights. So for people who have done this kind of thing, it looks an awful lot like a dot product when you write it out this way. But when we said linear combination, this was the linear combination we're referring to right here specifically. In fact, there are dot products if you like that kind of analogy. If you haven't heard of dot products, no worries, we're going to define this really carefully. So just a reminder, the product A times X is defined if and only if the number of columns of A equals the numbers of entries in X. Where the color coding, thankfully, is matching up the way we would like it to. Let's give this a try. I think we might have enough time to do it both ways, so let's see where we're going. First thing we want to do is look at the size of this matrix. It has 3 rows going this way, so we'll write down a 3 by 3 columns going this way, so it's 3 by 3, a nice square matrix. This one's a column vector, but it has 3 rows. I'll call it 3 by 1 since it's just 1 column right here. Later on, we'll extend this to a matrix times a matrix. So this could have been like 3 by 5, for example. Now, this whole rule right here can be majorly paraphrased. If those two things are equal, That's the number of columns in the matrix. That's the number of entries in the vector X. Then that tells us it is defined. In other words, we can proceed. If that was a 4 and a 3, it's undefined and we just stop. We just literally say undefined and we move on with our life. But you'll know it's undefined because if you try to force this to work, you'll realize either you ran out of entries X or you ran out of vectors A, and things are just not fitting together any longer if you try to force it in a case when it's undefined. So let's write this out. We take the entries in the vector X, here it is. It might not hurt to call this A and this X just to be specific. They become the scalars here, so we'll put in -4, multiply it by A1. A1 right here is just a shorthand for the very first column, 1, -3, 1. Plus, oh, and I got a little excited there. Grab the next scalar, 1. I mean, no change, but we really have to put that in there for the notes to be careful. That's rescaling the second column, -3, -4, 6. Plus 2 times scaling the third column over here, 0, 2, 1. And there it is again, folks. This is just nothing but another linear combination. If we were to work this out carefully, which we should, here's what we would get. Scaling the first vector is -4, 12, -4. Rescaling the second vector is fast. It's just multiplying by 1. So no change. Rescaling the third vector, the third column of A, gives us 0, 4, 2. Adding across the sides, we get cross entries in row 1, -7. Entries in row 2 are +12. And entries in row 3 are, looks like 4 or 8 minus 4 for a +4. -7, 12, 4. And we did it. That's our first matrix A times a column vector X. These instructions are practically verbatim right here out of the textbook. The textbook is going to ask you to do this twice on every single problem. And I want to emphasize right here, you don't have to. If you do it just once, that's good enough for me. We did it once. It was by the definition of A times X. And we're going to do it again a second time. The row vector rule for computing AX. This turns out to be the most convenient way to do it. We did it this way just to see how the definition goes. But if we did it this way every single time, you might actually literally run out of paper when it's a matrix times a matrix. So we need a faster way to do this. And I'm noticing I have 2 minutes. Maybe let's illustrate it just briefly, and we'll come back to it when we are in class next Tuesday, so it doesn't feel like we're rushing through this as fast as possible. So just a preview for what we want to do in next class. This is the highly encouraged method 2, row vector rule. Really, for those who have dealt with dot products, it's just a dot product. Take the dot product of row 1 with this one column and write down the entry. Your job is done. So let's write this out. What I mean by that is, here's our focus right now. I should use maybe just this color right here. Take the entries in this row, more corresponding to the entries of this column, and multiply. It'll be 1 times -4 for a -4, -3 times 1 for now a -7, plus 0 times 2, just a -7. Notice that matched up. Then we move down to the second row. Take entry -3 times -4, we're at +12. -4 plus 1 takes us to a +8. Sorry, my arithmetic stopped. 2 plus 1, that'll be, hang on, let me try again. -3 times -4 is +12. -4 takes us to -8. 2 times 2 plus 4 will take us to the 12. Yeah, my arithmetic did stop working there. I guess we're on the last minute of the class. And then tried it out again. We'll redo this when we're a little bit more fresh just to emphasize the rule. I feel like we're rushing through this one. Take the entries in the last row, match them up with the entries in the column, and multiply. That'll be -4 plus 6 for a +2 plus 2 for a positive, hang on, plus 2 for a +4. So that would be our result there. Does that make sense to folks seeing it that way as a shorthand? Okay, I notice we're a half a minute over time. Sorry about that. We'll come back to this again. I feel like we're rushing through that one. We'll look into a couple more examples just to drive the idea home. And that's where we'll start class on Tuesday. But any last questions, folks, before we call it a day? Okay, looks like I owe you all about a minute of time. We'll kind of balance it out with next class. But have a good one. If any questions come up over the weekend, don't hesitate to reach out.
Hey, Mike.
Thanks. Yeah,
Uh, I know we were talking about span, and my question kind of makes sense, but yeah, I'm in calculus 3 right now, and it just kind of seems like it's a way to describe a vector in all that space. Maybe not points, but just vectors in general.
yeah, basically that's pretty much what it's all about. A span could be just the origin, or it could be a line, a plane, and so on. And span is just saying all vectors that belong to the plane and so on.
Yeah, because that's what it seemed like. It was just like, oh, different scalars, sure, but it all seems like it's going to be on the same plane anyways. So
Exactly, yeah. And that's a big upper hand. Being able to kind of see it in the calculus 3 way means you really have probably a better picture than the average student in this class of what a span even looks like.
well, it's kind of confusing because the vectors are usually written horizontally. So like,
Exactly.
because we're doing like the
Brackets that
cross
way.
product right now, so it's ijk, and then you'd have your two vectors underneath that written
And
in
then
a
you're doing
like XYZ mode or like method. But
yeah. Yeah, that's exactly how we would actually come up with the equations of those planes from which those two vectors were spanning.
all right, well, thank you. I like that's just what it looked like to me, and I was like, oh, that just seems like we're just covering every vector in a possible, like from the origin in a possible like x1 x2 plane. So
Yeah, exactly.
have a good one, Mike.
You too. Take care.